Hello, AP Chemistry. How are we doing today? Hopefully, y'all are doing well. So, today we are going to be continuing our Unit 7 notes on equilibrium, and specifically, we're going to focus on solubility equilibrium. Now, in this, we are going to be covering Unit 7.11 and 7.13 in terms of the College Board calendar. So, use that as a reference for you when you're going and doing those practices on College Board. All right. Okay, so solubility equilibrium. Now, one thing that you'll find is that a lot of what we talk about in today is going to be very similar to what we've done with equilibrium in the past. So, what is solubility equilibrium? So, basically, what it's doing is it's going to be looking at the overall solution and trying to figure out whether or not the solution is saturated or supersaturated or unsaturated. And actually determining what those molarities or those concentrations are in that reaction, and finding the equilibrium constant in those reactions as well. So, first off, to do solubility, we need to remember what solubility actually means. Now, remember that solubility is when we're talking about that dissolving in water and actually creating those ions. We know that when we've got saturated solutions, one thing to note is that we do talk about these things called insoluble salts. In solubility equilibrium, one of the things that we recognize is that the things that we classify as insoluble are actually just a little bit soluble. Okay, and so when we talk about things that are insoluble, for instance, silver chloride, if you remember your solubility rules, chlorides are soluble unless they're paired up with silver, lead, or mercury 1, right? And so if we see those chlorides and we see it paired up with silver, we would immediately say, okay, well, that's a solid. It's not going to actually be soluble. It will not dissolve in the water. And in chemistry, we actually know that that's not 100% true, because while it doesn't dissolve much, it will dissolve just a little bit. And so I do want to make a note of that, even though we classify it as insoluble. So even though we say that it will not dissolve, we have to say that at least some will dissolve. Now, when we are looking at KSP, so KSP would be the solubility product constant. And basically what this is this going to be the measure of solubility in a solution. Okay, so basically the measure of solubility of a specific, typically the insoluble salt in that solution. Now, we actually can't compare your KSP values directly if the number of ions in the solution or in that formula differ. Okay, so if we've got the same number of ions, that works, but if we don't, we cannot compare it. One thing to kind of make things easier is that if you've got a smaller KSP value, it can indicate a lower solubility, a lower ability for something to actually dissolve. All right. Now, let's take this solution here. So for a saturated solution of AgCl, the equation would be AgCl, which again, we know that this is an insoluble salt, right? But we know in chemistry that it will actually dissolve to some extent, okay? And we know that silver chloride is actually made up of ions. It's made up of a silver and a chlorine ion. So that's what we see here. They both dissolved. And then they do tell us that the KSP of silver chloride is 1.6 times 10 to the negative 10, okay? So it is a very, very low number. Now, what this means that if the product of silver and chlorine is less than 1.6 times 10 to the negative 10, the solution is unsaturated. Basically that we would see no solid present. So if we get that concentration to less than the KSP, the solution is unsaturated. If it's equal to that KSP, then we've got a saturated solution, but it's perfectly saturated. So again, we wouldn't see any solids present. Now, if we have more than that amount, then what we'll see is that it becomes a saturated solution, and so we would actually see those solids that precipitate start to form. So when we go through these reactions, one of the things that you might not have known is that even if we add just a little bit over that KSP value, we're going to start to see that precipitate form. But if we take that same reaction and we add a very, very small amount, we won't see a precipitate actually happen. okay? And so that's something that we're solving for when we're talking about this solubility equilibrium. Okay, now the products of the ions, okay, so the products of the ions raised to the power of their coefficients, which again, that's basically how you would solve an equilibrium expression, right, is called the ion product quotient. That's your Q value, right? We've talked about the Q value. And if your Q value is greater than your KSP, we know that the precipitate will form. Why? Because we've got a higher value than your KSP. If it's less than your K value, then you're not going to see that precipitate form. Again, why? Because you've got a lower value than your KSP, right? You've got a lower concentration, and so we wouldn't see that precipitate form. Okay, it would be an unsaturated solution. Okay. If it's equal to it, again, would we or would we not see a precipitate? We would not. Why? Because if they are equal, then that would tell me that we are at equilibrium, and so there would be no precipitate formed, but it would still be a saturated solution. Okay? All right. Now, let's actually get into solving for these KSPs. So first off, the product expression for silver chloride would be this. Okay, I'm going to go ahead and rewrite the equation that we used earlier. So I have silver chloride, which we know is a solid, and this is a reversible reaction, and it will produce the silver ion and the chlorine ion. Okay, well, now it's basically solving for that equilibrium expression, right? So for my KSP, we know that it is products over reactants, concentration of your products over concentration of your reactants. So when I look at my KSP, it says KSP equals the concentration of silver times the concentration of chlorine. Why is silver chloride not there? Well, it's not there because it's a solid, right? And so we know that we don't take into account those solids in our equilibrium expression. And so when we're writing our KSPs for these insoluble salts, that's what we're going to be keeping in mind, is that that solid doesn't take a factor or is not a factor in your equilibrium expression, your KSP. All right? Okay. Now, again, this is just basically what I just said. So the silver chloride is left out since solids are left out of equilibrium expressions because they're going to be at that constant concentration. So what I want to do is I'm going to start, and it says write a balanced equation and the solubility product expressions for the following compounds. So here I've got copper bromide, and this is going to go to form a copper ion and a bromine ion. So when I would write my equilibrium expression, again, remember it's products over reactants. So my KSP equals the concentration of my copper times the concentration of my bromine. Okay? And that would be all we do for that. So now I'm going to do this one right here. So I'm going to do D, where it says Ag2CO3. First off, we need to write our equation. So I have silver. Now this time there are two of them, right? So we would need a coefficient plus our carbonate, which has a -2 charge. And when I write my equilibrium expression, what would I do? I know that my KSP is going to equal products over reactants. So my products are silver, which has a coefficient of 2, and carbonate, which does not have a coefficient. And so this would be my KSP. This would be that equilibrium, that solubility equilibrium expression here. Okay, so the solubility product equilibrium. Solubility product equilibrium, that expression that we have for this reaction. Okay, so what I want y'all to do is actually give B and C a try. So go ahead and solve for B and C, and then we will go over it. All right, so this is what you should have ended up with this zinc oxalate here. So I have, first off, I wrote my reaction. So I have zinc with a +2 plus the oxalate there, which has a -2 charge. And so we would find our KSP equals the concentration of zinc times the concentration of that oxalate. All right. Coming over here to our silver chromate. So here I would have silver. There are 2 silver there, so I would have a coefficient of 2, plus our chromate, which would be a -2 charge. So our KSP would be the concentration of silver squared times the concentration of that chromate. All right. Y'all, so I'm going to go ahead and leave E and F for y'all to do as practice, and we're going to go ahead and move on. Okay, so when we're doing these KSPs, there's 4 main types, 4 main ways to solve for your KSP. All right. Now, in this set of notes, so for today, we're only going to cover 2 of those. Okay, so next class, we're going to finish this KSP, this solubility equilibrium up. Okay, but for today, we're going to cover just 2 of them. Now, before we actually get started on these types, one thing I want y'all to note, and I'm actually going to write it here because it is important. It is a common way that you can get tripped up with your KSP problems. So my note is to watch your units. Okay, so watch your units. And by that, I mean, when you're asked these questions, sometimes you'll be asked to solve for molarity, right? Your concentration, which is moles per liter. But they might also ask you to solve for grams per liter. Or they might give you the problem and it be in milligrams per milliliter, right? And so you do need to make sure that you're converting into that concentration that they're actually asking you to solve for. Again, if they just want you to solve for molarity, you need to solve for moles per liter, right? And so keep that in mind. Again, I'm going to write that molarity equals moles per liter. And I cannot emphasize that enough because I can't tell you how many times that there have been mistakes made on this because a student forgot to convert that into whatever they were asking for. All right? Okay. So here is the first type of KSP problem that we could see. And so it says, given the molar solubility, find KSP. So in this case, they're actually giving you your solubility, and you're solving for your KSP. Well, this is actually the easiest way. Why? Because all they're doing with this is they've already given you your concentrations, so then you would need to solve for your KSP based off of those concentrations. So here it says the molar solubility of silver sulfate is 1.5 times 10 to the -2 moles per liter. Calculate the solubility product of salt, or of the salt. So first thing I need to do is to write my equation. So I have silver sulfate, and we know that this is a solid, and it's going to go to form silver, and there will be, silver, there's going to be a 2 here in the front, and sulfate, and there's not going to be a 2 there in the front. Okay? Then I would need to write my KSP. So that KSP expression. So my KSP equals the concentration of silver, and we're going to square that times the concentration of my sulfate, like that. Now, here we were told that they gave us the concentrations. Well, one thing to keep in mind is that you've got to think about your mole-to-mole ratio here. So they gave us the molar solubility of silver sulfate. So silver sulfate was 1.5 times 10 to the -2 moles per liter. And again, this is for my silver sulfate. Okay? But the problem is we need to find the concentrations of the silver ion and the sulfate ion. So for that, we're going to need to make some conversions, make those mole conversions over there. So I drop down moles of silver sulfate, and I'm going to go into moles of silver, and we know that there are 2 silver for every 1 silver sulfate. And so we would solve for our concentration of silver, and it would be 3.0 times 10 to the -2. moles per liter. And that would be for silver. So we would plug that in. Now, looking at my sulfate ion, we know that that ratio is a 1-to-1 ratio. And so we could just use our concentration, that molar solubility that silver sulfate has for our sulfate, because it is a 1-to-1 ratio. So now I just plug in my numbers. So my KSP equals, I found that the concentration of silver was 3.0 times 10 to the negative 2. I'm going to square that. And the concentration of my sulfate was 1.5 times 10 to the negative 2. And then we're just going to plug in those numbers into our calculator and solve, and we'll find that our KSP equals 1.35 times 10 to the negative 5. And that would be our answer. Okay? All right. So now, based off of that, I actually want y'all to come in and give this next one a try. So it asks you to solve for the molar solubility of MnCO3. What is the KSP for MnCO3 given the molar solubility? So basically just what we did, but this time you're going to be working with a different compound. So go ahead, pause your video, solve that problem, and then we'll go over it. All right, so here is what you should have ended up with. So you should have found that your KSP was equal to 1.8 times 10 to the negative 11. How did I get there? So first thing that I did was I wrote my balanced equation. After that, I wrote my molar solubility, so that solubility product expression, and I found that KSP equals Mn plus 2, so the concentration of Mn plus 2 times the concentration of CO3 minus 2. I plugged in my numbers, and I just used the molar solubility that they gave us because the ratio is 1-to-1-to-1. And so I found that KSP equals 4.2 times 10 to the negative 6 times 4.2 times 10 to the negative 6. Plugged that into my calculator, and I got 1.8 times 10 to the negative 11. All right. So I am actually going to leave these next 4 problems for y'all to do as practice. All right. So you can always come back in and double check these later, but I wanted to leave these as practice for y'all to do. Okay, so the second way that we can solve for our KSP is actually given KSP, so solving for these the solubility equilibrium. So given our KSP, we actually solve for our molar solubility. Now, basically, with this one, we are going to have to use a Rice table. All right. So it says calculate the molar solubility of calcium phosphate. They tell us the KSP of calcium phosphate is 1.2 times 10 to the negative 26. So what do I need to do? First thing, this is Rice. So first off is to write our reaction. So I have calcium phosphate in a reversible reaction, and it is going to produce 3 calcium ions and 2 phosphate ions. All right. Now, here's something to note. Again, this is a solid, so we do not take it into account when we're doing these Rice tables or when we're doing anything with equilibrium, right? So again, this is solid, so we won't take it into account. Now, initially, we're going to have 0 of our products. Now, how's that going to change? It's going to increase by 3 times. Why 3 times? Well, because we got a coefficient of 3. Phosphate is going to increase by 2 times. It's going to change by 2 times, right? And then for my overall equilibrium, or when we would hit that molar solubility, we would be at 3x and 2x. So then, now that we've got that, let's go ahead and write our KSP expression. So KSP is the concentration of calcium raised to the 3rd power times the concentration of phosphate raised to the 2nd power. And then we were told that KSP is 1.2 times 10 to the negative 26, and that equals calcium, which was 3x cubed, and phosphate, which was 2x squared. So then 1.2 times 10 to the negative 26 equals 27, not 9, 27, common mistake there. It's 3 cubed, not 3 times 3. So it would be 3 times 3 times 3. So we'd get 27x cubed times 4x squared. And when we would rewrite that, combining those two, 1.2 times 10 to the negative 26 equals 108x to the fifth. Divide both sides by 108. And when we do that, we will end up with 1.11 times 10 to the negative 28 equals x to the fifth. So then we do the fifth root of those. Or if you don't want to do the fifth root, you could take all of this and raise it to the power of 1/5. Not half, fifth. All right, I would plug that into my calculator and I would find 2.6 times 10 to the negative 6 moles per liter. So my molar solubility would be that 2.6 times 10 to the negative 6. Now, if they did ask you for a specific thing there, other than just the calcium phosphate, then you would need to make sure to remember your coefficients. So if they ask you what is the molar solubility for calcium, the calcium ion, then you would have to take that solubility there and multiply it by 3. Okay? All right. So what I want y'all to do is go ahead and give this next one a practice, and then we will go over it. All right, so here is what you should have ended up with. So first off, I did my rice table. I had that silver cyanide. It produced a silver ion and a cyanide ion. So our initial amount was 0 for both. Our change was x. So then when we reached that equilibrium, that solubility, then we would have x and x. We saw for our KSP, which would be KSP equals the concentration of silver times the concentration of cyanide. We would plug that into our equation. We plug in our numbers. So 2.0 times 10 to the negative 12, which is what they told me KSP was, equals x squared. And then we do your square root of both of those sides, and we would get 1.4 times 10 to the negative 6 as our concentration. All right. So I'm going to leave the rest of these for y'all to do as practice. But otherwise, that is it for our first set of notes on solubility equilibrium. As always, y'all, let us know if y'all have any questions, but otherwise, y'all have a great rest of the day. Bye, y'all.